Hey everybody, welcome back to our continuing discussion of non-visual senses. This time we're talking about the auditory pathway. Okay, so the auditory pathway picks up with where we left off last time. So your hair cells are supported by bipolar cells, so the stimulation of those hair cells leads to depolarization of those bipolar cells. Those bipolar cells form cranial nerve 8, their axons form cranial nerve 8. So cranial nerve 8 first makes its synapses in the cochlear nuclei, found here in the hindbrain. Then the next synapse takes place in the superior olive, which is a group of nuclei in the medulla, which is involved with the localization of sounds, so really low-level processing type stuff. The next synapse is in the inferior colliculus. Then the information is passed on to the MGN, the medial geniculate nucleus of the thalamus, where it is then passed on to the primary auditory cortex, and from there we'll go on to association cortices of various types. So to go over that, auditory nerve has a synapse in the cochlear nuclei, then on to the superior olive, and then up to the inferior colliculus here, then to the MGN of the thalamus, and then to the primary auditory cortex. So your auditory system has what is called tonotopic representation, which is a really cool property. It's really handy that it exists because it has allowed us to develop things like cochlear implants. So what I mean by this is we've got topographical mapping of different sound frequencies in both the cortex and the basilar membrane. So there are regions of the basilar membrane of your cochlea. Remember that membrane that houses all of the hair cells that respond preferentially to different frequencies. That's not the end of the story. We'll talk more about that. But basically different areas of the basilar membrane are responsible for picking up different frequencies of sound. Likewise, there's an organization in the primary auditory cortex that follows frequency. So low frequency sounds are mapped all the way up to high frequency sounds. So this organization matches from apex to base of cochlea in terms of the frequency that that area of the brain responds to. So let's talk very briefly about association cortices within the auditory pathway. I'm not going to spend nearly as much time on this as we did in visual pathways, just sort of in the interest of time. But let's go over it pretty briefly here. So we have our belt region, which is the first level of the auditory association cortex, pictured right here. This surrounds the primary auditory cortex right here. We then have the parabelt region, which is the second level auditory cortex, which, like it sounds like, surrounds the belt region here. In black, we have the anterior stream of processing, and in red, we have the posterior stream. Again, we're not going to go as much detail here as we did with the visual system, but basically in a sentence, the anterior stream is more responsible for the analysis of complex sounds, so like assigning meaning to sounds and that sort of thing, whereas the posterior stream is more important for sound localization. So nothing can ever be simple, right? So we have a couple of different ways that your auditory system is coding the auditory information. So first is what we call place coding. Signals are generated at different locations on the basilar membrane depending on pitch. Pitch is then recognized by reading from the location the signals are coming from, right? So one piece of information is the location on the membrane that's being stimulated. So if we take our cochlea and roll it out and look along the extent of the basilar membrane, we see that high frequencies are coded near the base of the cochlea, whereas low frequencies are coded near the apex. That's not the only piece of information, right? In addition to the location that stimulation is happening, we also have a rate of stimulation. So we have rate coding. Hair cells that send signals, they send signals at whatever rate the sound is received. So if the sound has a frequency of 100 waves per second, it will send about 100 impulses per second. But as you know from our discussion of the action potential and things like the rate law, neurons can only fire so quickly. So what happens if we have a sound that's a very high frequency, like 15 or 20,000 hertz? There's no way that a population or that a single neuron can fire that quickly. It's just not possible. So how can we account for that? Well, we have the volley principle. This is the idea that cells can alternate their firing in rapid succession. So frequencies well above 1,000, signals per second can be achieved. So volley principle, basically a group of neurons is treated like one signaling unit, right? So while one neuron can only fire maybe 1,000 times per second, if they alternate their firing with a group of neurons, we can make that frequency represented much higher. So by a group of neurons alternating their frequency in a sort of volley, we can code for higher pitches. So, to sum things up, place coding seems to account for low frequency sounds well, while rate coding accounts for high frequency sounds, especially with the volley principle helping to account for high frequency sounds. A combination of the two tends to account for mid-range sounds. So unfortunately, hearing loss is a pretty typical human experience. There's two different kinds of hearing loss that we can talk about. There's conductive hearing loss, in which the sound is not reaching the inner ear. This can be caused by a number of things, including disruption of the ear canal, damage to the eardrum, or malfunction of the ossicles. So any number of things that are to do with that initial conduction of the sound waves into our inner ear, into our cochlea, can contribute to conductive hearing loss. This can often be treated with something like a hearing aid, if it's just a matter of amplifying the sound that will fix the problem, or surgery to repair damage or remove blockage. Sensorineuronal hearing loss is more difficult to treat. This is typically a problem with the inner ear, generally caused by damaged hair cells. This can be caused by something like exposure to a loud noise, damaging the hair cells, which cannot regenerate, a virus that might infect and destroy hair cells, or just as a normal part of aging. This can sometimes be treated with a cochlear implant. Okay, so a cochlear implant is an awesome little piece of technology. This consists of a microphone, which can be seen here, and a signal processor here, as well as an electrode array, which you can see is implanted here along the cochlea. So this electrode array is inserted into the cochlea and follows that snail-like curl around and rests upon the entire extent of the basilar membrane. So as we've talked about, because the basilar membrane has a sort of tonotopic organization, it's reliably organized in terms of what frequencies of sound it responds to, we can take advantage of that property. The electrode can then stimulate different portions of the membrane, which can stimulate that cranial nerve, the auditory nerve, to carry that signal on into our brain. So basically, we're bypassing the defective portion of our hearing system by using this microphone and signal processor to convert the sound around us into electrical signals, which we can then use to stimulate this electrode array, bypass the damaged cochlea, and give rise to the perception of sound, which is just awesome. If you're all having a bad day and you want a little pick-me-up, go onto YouTube and search for people with cochlear implants turning them on for the first time. It's pretty moving, especially if you find babies having cochlear implants turned on for the first time and sort of hearing their mother's voice for the first time. Super cool. If you need a little pick-me-up, go check that out. Okay, so a brief word on the sound perception of loudness. So loudness is reflected as the psychological quality that we experience for higher amplitude stimuli. So sound waves with big amplitude waves are perceived as more loud. This happens because a greater number of hair cells send signals to the brain. So more hair cells in the region are disturbed and send that signal to the brain. Whereas soft sounds activate only certain hair cells, right? So you can think about loud sounds activating those hair cells plus more nearby surrounding hair cells at the same time. So loud sounds cause a bigger disruption in that membrane, stimulate more cells to fire at the same time, whereas soft sounds only stimulate a section of those cells. Okay, that's it for the auditory pathway. Next time we're going to talk about auditory perception.